Okay, so this is supposed to be the continuation of the previous example on MIPS architecture where you saw a load and store instruction. I think we practically saw that in memory, right? And you're fully convinced if maybe you don't really understand it. Some of the instructions shown there were not exactly here, right, as shown here. And that's because of a simple thing. Those register initializations um, were not part of this code. This code is just to access and increase it by each, right? It's not to do the initialization of the registers and everything. That's why that code looks far more complicated. But as time goes on, you get a hang of it, right? So never mind. Then we come to another example, right? And next time we want to swap. Okay, this is a C function. And I think we are taking an array as an input and we are taking a key. Now we declare a variable called temp, right? We store that variable, the keyed element in temp, and now we swap. So let me show it. So example, if you have 1, 2, 3, 4, and 5 stored in the array, and assume k is 3, right? So here the initialization is what? First initialize temp. Okay, if initialize, it just means create a variable. So let's assume k is 3 is equal to 3. So we've created it. The next part is say temp is equal to v of k, right? Now let's assume that we are using zero index base, right? So v of k, where k is equal to 3 means k, v of k will be equal to what? So v of k will be equal to, this is 0, 1, 2, 3. So v of k will be 4, right? Now the next line is that we are assigning v of k, which is the memory location. We are assigning it to what? V of k plus 1. So v of k was this 4. Now we are saying that it should be equal to v of k plus 1. So this 4 will change to 5 now, right? After this line. And now we are assigning v of k plus 1. V of k plus 1 is this 5. We are changing it to what? Temp. Remember, temp is storing 4. So now temp will now become 4. Simple as that. We have been able to swap. Now let's see how we do it in assembly, right? So we are using MIPS assembly. Now here you see we have some swap. This is usually called a label, right? And it is used when it is for code like when you have let me say lines of code which you know you deem them as useful, right? You don't want to be repeating yourself every time. So yes, that something like that. Yes. So like these lines of code, they are useful, right? But I don't want to be repeating them every time. So I can just tell the processor to go here, read these lines of code and execute them. It's similar to a function actually. That's what a function does. Right. So that's the abstraction. So this one is understandable. Now the first thing is they are using a multiply immediate instruction, right? And what they are doing is that they've taken register 2, right? And they are multiplying uh, the content of register 5 and by 4, and they are storing it in register 2, right? So what I'm guessing is that register 5 is storing key, right? Yes, register 5 is storing key. So assuming that we are using this old example where key was 3, then it means that here will be what 5, here will be 3 times what 4, right? And 12 is what will be stored in what $2, right? Yeah, so that's for the first line. Now the second line, they are adding $4 and $2, and they are storing it back in $2. So remember, in the previous line, $2 was what 12, right? Now what is $4? Now the $4 they did not state any use case, but I'm assuming it's for the base address of the array. So the base address of this thing, right? So if that is the base address of the array, then it means that that base address will be adding the content of what's $2, right? And will be replacing the old content of $2 by that results, right? So let's assume that the base address, which is $4, was something like 0x 0.08, right? Then we'll be coming to add $2, which is 12. So 0x08 plus 12, right? That's I think 20, right? So 20 in hexadecimal, and that will be stored in here. Right, but don't worry much about that. So, but that's what the instruction is doing. Now, the next part is a bit crucial, right? So the next part is where, should I say, the swapping magic begins, right? Now, you have been able to calculate the address where you are supposed to go and fetch the kth element from, and that is what is stored in $2 right now. So you have been able to find the correct offset and where to go and fetch the kth element from the array from. This line is actually the fetching, right? You see here in the C code, the address and the fetching is all abstracted into one line. So you don't appreciate it. But when that is what actually the machine does, the machine actually has to find the offset and also has to find the address and also fetch it, right? So it has found the offset and address, computed it into S2. So now it's now going to fetch it. So when it's going to fetch it, remember, in the first part, we were picking exactly from K, right? So the content stored in $2 will not offset it, right? Because it's that exact address that we are taking from, right? So we'll take that exact content in $2 and store it in $15, right? That's the load word instruction. Now, when we are done with this, then we go to the next part. Then now, see that same $2 address, right? That same $2 base address we calculated, we will not be picking from the zero part. We're picking from what the next word, right? We were picking here was what k plus 1. So here the next word would be what plus 4, right? Because words are what 4 in MIPS. So we'll be picking from k plus 1, and I'll be storing it in what $15. So now you see we have $15 storing what k v of k, and $16 storing v of k plus 1. Now we have to store back. We have, you see, $15 and $16 are registers. They are not memory, right? So we have to store it back into memory. To store it back into memory, we use the instruction called store word. So the store word instruction works like this. You show it where it is supposed to pick what to store and which part of memory it should store it, right? So now we are picking from $16. Remember, $16 is storing v of k plus 1, right? According to what we have discussed. So we are picking $16. And now instead of storing it back into what 4 offset $2, we are storing it into what 0 offset $2. Have you remember? Do you remember that 0 offset $2 was what where v of k was located? So we have swapped that part. Now we're also picking from $15 and we are storing it into what 4 offset of what $2. Remember, 4 offset of $2 was where what v of k plus 1 was located, right? So now we have what also swap that, right? So these two instructions, these, should I say, four instructions, um actually affect the swap, right? The rest are just for calculating the base addresses and doing what's necessary. Now this, like I said, is a routine. So when you finish, you have to jump back and continue your code. That's what you see the jump register there for. So the last one is just to say return, right? Yes, and in C code, because I'm sure that probably here was void, so they did not put a return bar. Assembly will require you to do it specifically. But that's as short as that. I don't think you need a simulation to really understand it. It's quite basic. So the next part, we've realized few things in MIP, right? It says MIPS loads in words, right? But the addressing is in bytes, right? So MIPS addressing is in bytes, but in loading it's words. So MIPS sees addresses as bytes, right? So MIPS, you have byte 0, byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, up to byte 2 is the power 32, right? But in words, we have word 0, word 4. We don't have word 2. That's it. And we have also seen arithmetic on registers only so far, right? And these are some of the arithmetic instructions supported by MIPS and how they are being interpreted here. Now, here is how you may wish to view your program being translated from MIPS back into real machine language, right? So at the high level, you declare variables and everything. Right now, what you have is actually between them is a compiler. So the compiler will actually produce, if we are compiling for MIPS, to actually produce this MIPS code, right? And now this MIPS code will be assembled by something called an assembler into zeros and ones. Now, this load word has a specific, how do you call it? A specific opcode. It has this T0 has a specific number assigned to it, right? So it will take them one by one and transform them into their respective numbers. And that's what you see. Mostly they'll give you a table for you to know the correct assignments associated with this, right? So don't worry much. But these lines, so line 1 corresponds to this line. This is how the instructions are stored in memory. So um, load word, assuming that the opcode is the first 4 bits, right? T0 may be the register T0, it is represented as what 1001 in MIPS architecture. Then the remaining will be for the offset as well as the what second register. It's more of advanced stuff. So when we get there, you will know about it. But just know that each line here is actually in machine language represented as a bunch of zeros and ones, which you should know about. So just in case you are so interested in viewing the MIPS word um, architecture, the MIPS memory architecture, here it is. So you realize that a word is what 4 bytes, but within a word we have what 8 bytes, 8 bytes, 8 bytes. Now remember this is hex, so each two digit is 8 bytes. So 8 bytes, 8 bytes, 8 bytes, and this is word 0, this is word 1, word 2, word 3. The words are what that, but this is byte 0, byte 1, byte 2, byte 3, like that, and you'll be going forward. So that's basically it. And once you get these ones, then the addressing and fetching of MIPS, fetching of data in MIPS won't be so confusing. And I also think this is also representative of the same thing we've been talking about so far. So for example, if you are storing a variable in A0, right, in MIPS it will be assigned 4 bytes, so 1, 2, 3, 4, right, yes, and all of these 4 bytes will be used to assign the variable. A1 is as you can see and A2 as you can see, so it's a matter of the view of the registers and how they are stored in memory. And there is also a bit of talk about the endianness. I think a little question would solve that. So let's see. So it says in little-endian machines, bytes are numbered starting with 0 at the least significant bit end. Word addresses are the same in both formats and refer to the same 4 bytes. Only the addresses of bytes differ. So let's take an example. So let's say you have something like this, 0 1 1 0 1. Now if you consider Big-endian, right, just like the name sound, Big-endian would give the least significant bit a very high bit order, right? So Big-endian will label this as what? Bit 0, this as bit 1, this as bit 2, this as bit 3, and this as bit 4. Little-endian will do the opposite. It will label this as bit 0, bit 1, bit 2, bit 3, bit 4. Now what is being said here is that no matter how we are doing the labeling, when conceptualizing access of memory in terms of word, it doesn't affect it because after all, we are picking the whole thing. So we don't care where we are, where is the most and least significant bit. When we are conceptualizing memory in terms of bytes, right, then there is a problem. Are you saying that byte 0 is referring to the far left or byte 0 is referring to the far right? Right. So in that case, it should usually be stated for you. So, and the question is that suppose that um $0 dollar $S0 initially contains this number, right? Now, after the following program is run on a big-endian system, what value does $S0 contain? Now, what about an little-endian system? So let's see. So the question starts with you having 0x 2, 3, 4, 5, 6, 7, 8, 9, and this is in hexadecimal, right? Now, usually the simplest thing you can do is just divide it into groups of bytes, right? So this is yes, so this is an hexadecimal. So every one of the numbers is what a byte. BSB one stop. Now, after the following is run on a big Indian system, what value does S0 contain? So realize that they try to run load bytes into S0, offset of $1, 0. So let's take note. Now, there's a little difference between $S0 and $0. $0 means zero itself, right? But $S0 means save register 0, right? So take notes. And $0, I'm thinking that $0 is referring to the word address. So this word has a word address of 0, right? This whole thing is a word in MIPS, and the whole thing has a word address of 0. Now, if they are saying it is having an offset of 1, and we are in a little-endian system, little-endian means what? The ending is the smallest, right? You have the ending as the smallest. So you make sure that in little-endian system, the ending, right, have the smallest value. So you realize that in little-endian system, all you have to do is label it starting from what? The least significant bit as 0, 1, 2, least significant byte, sorry, 3, right? So that's a little-endian labeling. Now you realize that we are loading from what? Offset 1, right? So when you are loading from offset 1, then it means that what? We are taking what? The 6, 7. So the bytes that will load will be what? 6, 7. And now since it's a 32-bit architecture, you have to make sure that you pad it with the corresponding 0 to make it what? 32-bit. Now, in the same scenario, if you rather had big-endian, it won't differ much. So you'll still have to divide them into groups of bytes, right? But in terms of big-endian, start your 0 from here. 1, 2, and 3. So in big-endian, I think I can leave it an assignment, right? So in big-endian, it will be what? 0, 0, 0, 4, 5, right? Yes, in big-endian. And I think with that is very much what you should know for a beginner introduction to me. Yes, and so yes. So as you can see, it's clearly differentiated in big-endian and little-endian systems, and you can see that over here, right? So next time.